Good morning, everybody, and welcome to day 2 of Forward from the Fields Medal. I promised to tell you if there are any changes to the program. I think we do not have any changes for today. There are 2 small announcements. One is that I want to say thank you to the AMS and to Springer Nature for the book displays, and you can go and have a look at those at any time and talk to the representative from the publisher about the books, or if there's anything you want to try to buy. And we are having a small or hopefully large fundraiser for our piano. The piano was a gift from Coxeter, and it was the piano he had as a child. So it's a rather nice piano, but it needs some work in order to be playable again. And it's very nice to have a playable piano in the atrium. So you can, there's a fundraiser, you can click on the QR. I mean, you should point your camera at the QR code and make a donation. You get a tax receipt through Canada Helps. And if anybody needs a US tax receipt, then it's better to do it through American Friends of Fields, which you can find on our website. Now I'll hand over to Ian so that we can start this morning's session.
Thank you, Deirdre. And trust anyone online will let us know if the sound's not coming through correctly. This is, I think, on. Yes. Oh, so a great pleasure to start the morning session with introducing Ulrike Tillmann. Born in Germany, came to the United States for her university education, graduated from Stanford University, and followed by a habilitation in Bonn. Foundational contributions to the moduli space of algebraic curves through centered around the Mumford conjectures, sort of famous work. Mention Ulrike's outstanding leadership role, currently director of the Isaac Newton Institute in Cambridge, formerly a president of the London Math Society. Other recognitions, perhaps we won't give a full list of such a great career. Maybe mention the Whitehead Prize, which is an early distinction for research. Fellow of the American Math Society. Anyway, a wonderful career. A great pleasure to have you here to speak to us about a Renaissance.
Thank you. Thank you very much. So I have to admit, when I received the invitation to speak in the mathematical physics section, I thought I don't identify as a mathematical physicist, and should I accept? And I thought about it for a while, and I thought, well, there is actually a story to tell, and maybe I can do that. Really, topological quantum field theories have been very influential also in my sort of topology, algebraic topology, homotopy theory. And of course, the origin of that is from Witten's paper in the late 80s, where he defined topological quantum field theory. So my idea is really to look at topological quantum field theories from a more topological, algebraic topology eyes, and then explain how also in the last 10, 15, maybe 20 years, it has really led to a completely different point of view, I think, and many breakthroughs in what I would call the algebraic topology of manifolds. So I should also say it's very much, of course, sort of a personal view, and I will go with a red thread, try to have a red thread through this. Of course, one can choose many paths through this, and many other things contribute to these things, but this is the story I want to tell. So to set the scene, manifolds. Manifolds are one of the most important things in algebraic topology. W generally compact smooth manifold of dimension D. And if you want to look at manifolds or any object really in mathematics, you also want to look at their automorphism group. So the diffeomorphisms of W are generally the automorphisms, and we want to understand those objects. Generally, we fix the boundary pointwise, but that's a detail for now. Now, Understanding manifolds up to diffeomorphism, that's sort of a classification theorem, but understanding the diffeomorphisms has been extremely difficult. Even in simple examples like the disk or the spheres, knowledge has been relatively sparse. And I will come back to that later on. So one early idea was actually to consider manifolds up to an equivalence class, namely that of cobordism. And two manifolds under this equivalence relation are cobordant if they together bound another manifold. So, and it's an equivalence relation, as you can see here. If I have one manifold M0 related to M1 via manifold W, and M1 is related to M2 via another manifold W prime, then I can glue those two cobordism W and W prime together. And now I see that actually I have M0 union M2 are bounding another manifold and hence are cobordant. And indeed, the cobordism equivalence classes are a group and even a graded ring. Now, the big breakthrough was actually via Tom in the 50s. Namely, he managed to actually show that these, putting all these cobordism groups together in a graded form here, in the non-oriented and in the oriented case, so manifolds come possibly with an orientation, and I can make the definitions to remember orientations. They are actually the homotopy groups of some spaces. And that's a quite amazing thing to really see that all of these classes, which are just defined abstractly, are the homotopy groups of one object. So studying one object, you can study all of the cobordism. And I will say a little bit more about these spaces later on. For now, let me just say they're actually relatively computable and easier to understand. And indeed, these turn out to be polynomial rings over Z2 and over Q. Well, rationally, they're polynomial over Q. And indeed, one can say that a manifold is cobordant to, or is a boundary of another manifold if and only if all the Stiefel-Whitney classes vanish. And similarly, in the oriented case, it's going to bound, or a multiple of it is going to bound another manifold if and only if all the Pontryagin classes vanish. So the citation of René Thom reads that he invented cobordism, and it led to most penetrating insights into topology of differential manifolds. And indeed, let me just put these four Fields medalists up in the following years. All of them really, cobordism was a very important part of their work. So for example, Latier, the first proof of the index theorem was via cobordism. I guess Novikov did a lot of work on cobordism theory later on, more computations and so on. Okay, so now in the, we have a pretty good idea of what manifolds are, and classification surgery theory helped as well. But things slowed down a little bit. The diffeomorphisms themselves were really hard to get at. On the other hand, 3- and 4-dimensional manifolds, which were hard in a different way. So all these theorems that most of the theorems that I mentioned before were actually, for example, Smale had the generalized Poincare conjecture that holds up for higher dimensional manifolds. However, in dimension 3 and 4, of course, things were much harder. But in the 90s, we do have Donaldson and Thurston, but also Fleur coming on the scene. And it was Attia, who suggested that actually, since Donaldson's invariants were defined using some mathematical physics ideas, the moduli space of instantons, and Fleur similarly used mathematical physics ideas, he asked the question whether they can be put somehow together, and is there an explanation from physics that would explain all these different invariants? And indeed, Witten then defined the first topological field theory using Fleur homology and Donaldson's invariants. Now, that's a very quick run through. I now want to start my talk properly and start with the definition of topological quantum field theory, and then come later to what I mean by the Renaissance. So topological quantum field theory, we start with the Bordism category. So here Bordism come in a different way. The category consists of D-1 dimensional closed manifolds. And now I consider as a morphism from one to the other given by a Bordism. So here we have a composition of two manifolds, two morphisms, one from M0 to M1 and M1 to M2, and the joint one gives me a morphism in this category. Now, this category also has a very natural operation, namely the disjoint union, and that gives me defines on this category a symmetric monoidal product. So what is then a d-dimensional topological field theory? I take this relatively simple Bordism category and map it, consider functors into vector spaces. So think vector spaces here, finite dimensional, indeed, and I want to take the union, the disjoint union, into tensor product. So this is now a functor of symmetric monoidal categories into the category of vector spaces. Now, the unit for disjoint union is the empty set. The unit for tensor product is just C itself, if we're working over the complex numbers. And so this already tells me that any functor like this will have to take the empty set to the ground field. Now the motivation, this is Attia's original motivation to define this, is now that any closed d-dimensional manifold gives rise to a topological invariant. Namely, a closed manifold is a cobordism between empty and empty. And so it defines a linear map from C to C, and that's just given by a number. And that number, by definition, will be a topological invariant. Right. So now the inspiration is, I guess, from physics here, namely locality. Topological field theory are supposed to be local. Locality already comes from taking a manifold and chopping it up into different parts of the cobordism that you might see, different morphisms. But chopping up a manifold this way to get the morphism, you might as well also chop it up the other way. And so what we get is here, we get manifolds with corners. And in higher and higher dimension, I will have higher and higher co-dimensional corners. But basically, ultimately, what one wants to do is one wants to start with points, have both arcs between points as cobordisms, and then I take surfaces between arcs and circles to get a surface, and between surfaces I get three manifolds, and so on. So I can build up a category which is now a so-called d-dimensional category, higher category theory. This is the most important example in that. And so I can actually define my cobordism category in this setting and take it and define extended topological field theories now in the d-dimensional category theory sense, and have a morphism or functor from the extended Bordism category to some d-dimensional category, which is symmetric monoidal, which is the replacement of my vector spaces. Okay. And the cobordism hypothesis, sort of following the physics, is that everything should be determined what I assign to a point. Okay, all these higher dimensional things should follow. Now, this is, was formulated by Bias and Dolan in the 90s, and we'll see where that leads us. So here's a very simple example of one-dimensional series. In one dimension, I only have objects named, the objects are zero dimensional, so they're just points. And in the oriented case, I need to distinguish between an incoming and an outgoing, a plus and a minus. So I have these two distinct points, and I have these morphisms here. An oriented arc gives me a morphism from a plus and a minus, and similar the opposite way. So I get, for example, here an evaluation that goes from V, which I might assign to the plus, and V dash applying to the minus point, into the unit of the tensor product. And similar the other way around, a co-evaluation here, and putting things together. This tells me I have this interesting map, and unraveling it means that my V is actually finite dimensional. And indeed, the circle, combining it, gives me a map from the empty to the empty manifold, or from C to C, given by a number, and it's actually the dimension. So with this here, it is clear now that actually V dash has to be the dual of V, and indeed everything is determined by what we assign to just one point. That's a very baby example, but remember the duality between V and V dash that we get automatically here for later on. Okay, so now the way it was, I defined it was a little bit vague, and indeed that here, when you considered morphisms, cobordisms, it was always up to diffeomorphism because you wanted topological invariance. However, that is very, very rigid, and homotopy theory doesn't work. The power of homotopy theory comes in when you allow yourself to have more flexibility. So we enrich our category here, and Ian mentioned moduli spaces of surfaces. This is exactly, if you do it in dimension 2, that is what you get, namely moduli spaces of surfaces, and it's really a version of Graham-Siegel's category of for conformal field theory. But let me just explain it in this context. Now, instead of just having, we now consider our manifolds, our objects, to be embedded in some large Euclidean space, and similar for both target and source. And my morphisms now are also embedded cobordisms. And there's, of course, a natural topology on these embedded diffeomorphisms. So it's takes the space of all these embedded cobordisms. So one can define this. You take embeddings that are, preserves those boundary conditions into a large Euclidean space. You mod out by the diffeomorphisms of W, which act on the embeddings by precomposant. And indeed, what you get is really the homotopy type of the classifying spaces of these diffeomorphisms. Okay. So now this is a very rich category, and you see the diffeomorphism come in very naturally here as well. Okay, so topologists have learned from Grothendieck and Siegel, I guess, that once you see a category, what you try to do is to study its nerve. Or that's what we know how to study. So this is a process that really assigns to every object a point. And I'm building up now a space. For every morphism, I give myself an interval between the 2 points. And for every commutative triangle, I have a triangle. And so build up my space one by one. So the nerve, or the realization of the nerve as a simplicial space, is what I call BC. And this has various properties. The first thing which is quite important in our context, is that, you know, the morphism F between A and B might not be invertible. But once you put a path between A and B, this topological realization is, of course, invertible up to homotopy, because you can just go from B to A by reversing that edge. So really, we have, we forget some information here if we just consider the homotopy type. Namely, we reverse all the morphism up to homotopy. However, this functor has some other nice properties, namely, remember our cobordism categories and also our target vector space categories had a symmetric monoidal structure. And this symmetric monoidal structure carries over to the topology side, but this time I get something, well, E-infinity spaces, meaning it has lots of, well, it has a homotopy abelian product space. Indeed, once we group complete all the connected components that form a group, form an infinite loop space. So this is a very useful thing. These E-infinity spaces or omega infinity spaces are actually sort of the abelian groups in homotopy theory, if that makes sense. Okay, right. So we were then able to actually compute the homotopy type of the classifying space of this bordism category in this enriched case. And okay, now this is a symbol, but notice there is the M. The M is for Thom's space, because these are really just Thom spectra. And the T is to remember that actually we remember tangential rather than normal information in Thom's original theory. That also may note that we have one of these spaces for every dimension D. So the D here, the bordism category, is reflected in of course, in this space here. Now, maybe it's worth going through very briefly the symbol. Again, the main point, of course, here is that we understand this space. And let me just very quickly say what this space is. So omega k just means I have based maps from a high dimensional sphere into my X. Think of it as grading merely in homotopy theory, or a shift of grading, I should say. These MTODs is a spectrum, and that's a collection of many spaces. And these spaces are just, one-point compactifications or Thom spaces of certain vector bundles, namely UDN perp, where UDN perp is the orthogonal complement of the universal bundle over the Grassmannian. So the Grassmannian of n-plane, d-planes in R d plus n. So these are all classical objects. They're put together in a way that we already understood from the work of Thom. Okay, so I also just written here Thom's collapse map, which takes a manifold, think of it as embedded in a large Euclidean space. You look at the normal bundle, you collapse onto the one-point compactification of the normal bundle, and then you push forward into this space that's defined here by, okay, taking a point on your manifold and a point in the normal bundle to the tangent space at some point and the normal bundle. And this tangent space in Thom's theory was generally the normal space. So it's very similar, but it helps us to, by this slight change, it means that we can look at every D separately. Now, I already talked about this extended version of a cobordism theory, where you started off with a point and built up more and more cobordisms between entire manifolds. You have a version of that, and it turns out to be literally just a shift. The sigma is just a suspension functor, and it's just a shift. Okay. Right, now, what I mean, what can we learn? I said, you know, topologists like to apply the classifying functor. What can we learn possibly from these classifying spaces? And indeed, an interpretation is really to think about invertible extended series. So what is an invertible extended series? By definition, one might say, well, this theory is invertible if it factors through this category here. And what I do here is I add all the, I force it to sort of be a group point, namely I add all the inverses, the Picard inverses of the objects, but also all the inverses of all the maps. So this is a sort of a Picard function. And then, of course, it has to land here into the invertible elements of it's a subcategory of whatever category I started off here, BD. Okay, so the map down here is really equivalent. Now we are in the invertible case, the groupoid case, that is equivalent to say having a map of infinite loop spaces on the classifying spaces or the underlying spectra indeed. So that's a translation in some sense of this. So really, this is used as this interpretation, or this is actually the suggestion by Fried and Hopkins. They now compute the map of spectra, homotopy classes thereof, and indeed they look at a specific universal target. The upshot, however, is, I don't want to go into details here, but the upshot is that they actually can compute certain invariants that the physicists were interested in, and they could check these invariants and compute many more. So, for example, TQFTs has computed these topological phases and many others. So this is possibly a very clear way of giving a machine to compute physical identities from homotopy theory, and possibly one of the few. Okay, let me move on. Let me go back to the cobordism hypothesis. Remember that said that the whole theory in the extended case is determined by what you assign to a point. Now, Lurie actually completely solved this case. Namely, he laid out a complete 100-page sketch of a proof of this cobordism hypothesis, where, remember, we had in the 0-1 case, we noticed that the vector space associated to a point and the one to the with the opposite orientation, they were dual to each other. And this can be, there's a generalization for higher categories. And so not only do we have that it is determined by a point, by vice versa, whenever we find an object in VD that is fully dualizable, we can construct such a function. So in other words, the field series, topological field series in this settings are completely classified as well. Namely, start with an interesting category, look at the fully dualizable objects in it, and each of them give you a topological field series. That has been a very powerful theory and has been used by many to construct examples and understanding. Now, just to go back to the invertible series, it is actually a very easy exercise that the extended cobordism theory, which are framed, and I have to, I forgot to mention here that we need to have the framing. So whenever you have the time, we have to consider different tangential structures, but the points have to be framed like in the zero-dimensional case. I have to know which way I go, left or right. And in higher dimension, I need to have a frame around the appropriate frame, namely d-dimensional frame around the point in order to make this all work. But the framed cobordism theory is, of course, well known to be stable homotopy theory. So in other words, this space here is just the infinite loop space on a single point. And of course, since we have to have maps of infinite loop spaces, the cobordism hypothesis here is kind of trivial. You have to take the point, assign something to it, and of course, your map will be determined by that. Okay, right. So this is a sort of a walk through the topological field theory. Now I want to come to the part which I would like to call the Renaissance or Renaissance for algebraic topology for manifolds. Okay. Now, there are some key results that I want to state, and then try to explain why that actually led to some somehow really different approach to what we had before. So let me start with defining this manifold WG1. You take Sn cross Sn. So that's a 2 n-dimensional manifold. So I'm just going to talk about even-dimensional manifolds and for the rest, almost. And I take connected sum of these. And then I take one disk out, so I have a boundary. Now, note that if I do this for n equal to 1, then I'm just constructing a surface of genus G. Now, Galasius and Van der Williams showed that if I look at the diffeomorphism groups of these manifolds, sorry, I also take an arbitrary closed n-1 connected manifold, and I take connected sum. So in particular, this is already interesting when W is just the 2n sphere. But I take now the limit by just gluing in higher and more of these Sns cross Sns. So I have let G, the genus, effectively go to infinity. And what I get is a map from this classifying space of diffeomorphism groups into this Thom spectrum again. So remember, these are supposed to be easy and we can compute with them. And the point is that they show actually that indeed, this map is an isomorphism in homology. So we really understand, therefore, the homology of these spaces once you take G to infinity. Luckily, they also prove a theorem that actually these homology or cohomology groups are independent of G once the genus is high enough. So in other, for G large enough, I actually don't change the homology. So that means actually understanding this final term, I do also understand a lot of these terms for finite G. In particular, they can also compute precisely, or it's a straightforward computation actually, what the cohomology of these spaces are. And so you have effectively here the characteristic classes of.
You can have your breakfast now.
What was that? Okay. Sorry, I didn't hear that. Okay, I wasn't. Okay, great. Okay, so we have a complete computation and we understand now these characteristic classes for these particular manifolds. What is the idea here? I should mention actually in this context the manifold conjecture. The manifold conjecture precedes these theorems, but and it is the case when n is equal to 1. And in well, let me just go on the way Soren and Oscar proves this theorem is actually by considering the theorem we had before, namely the calculation of the Bordism category as this infinite loop space coming from the MT spectra. Now, what is roughly the idea? When you look at the Bordism category, you consider all d-dimensional manifolds, all of them, connected, non-connected, and so on. And altogether, sorry, they form we have this homotopy type, get this homotopy type. What the idea of Galasius and Oscar and Williams is that you make that category smaller. So you make it so small that you basically just have a limit of these manifolds that you're interested in. And each time you have to prove that making the category smaller doesn't change the homotopy type. This is very much a cartoon of what they're doing. It's a quite complicated theory, and the new tool is really parameterized surgery in that context. Okay, so let me go on now. I think this is the key result. And then we have a beautiful vibration, the Weiss-Küppers fiber sequence. This is Alexander Küppers, might be known some of you. And let me explain that. So what I do is you take the boundary of my manifold W, and I divide it into parts, and one part I call M. So in this case, maybe this is my M, and this whole thing is W. And then I look at, well, I can, of course, look at the diffeomorphisms of W relative to the boundary completely fixed. Or I can look at embeddings of W into itself, where I only fix part of the boundary, but not the part that is relevant to, comes from M. Now, this map here is just one inclusion, actually. But the homotopy fiber, it's not too difficult to see that that is actually the diffeomorphisms of M cross a little interval. So basically this light colored shape modular its boundary. So we have this fiber sequence, and indeed the diffeomorphism of M cross an interval, I can just put another M cross an interval next to it, and I have a product on these. And that gives allows me to do loops. And this is actually something that Alexander noticed. So we have this fiber sequence, and I can now work with this. Now, you might say, what do I gain? Looks still complicated. Well, first of all, remember, look at this. W can be, if I'm interested in M, and the disk is already interesting, then W, I can choose anything. In particular, I can choose it to be the WGs that we just tried to understand. And then the embeddings, well, there's another big machinery that can be used, namely the Goodwillie-Weiss embedding calculus. So basically, we're saying we understand this, and we understand this. And so we can also then understand the third term, sort of a exact sequence, homotopy exact sequence. So Küppers, for example, used this to prove for M equal to just a disk that these diffeomorphism groups have finite type. So that means finitely many homotopy group, finitely generated homotopy groups in every dimension. That wasn't known before then, which is actually surprising. Right? It's very very basic thing you might want to ask. Similar, you can prove a similar theorem for M closed in and its diffeomorphisms. So, okay, let me move on. Now, this is an important one. Also, note, if you then know, once you then have gained information here, and you might know this term, then you can now again understand this term. So you can play these sequences one against each other and learn more and more. So one example, this was an application. This is where the Weiss came up with this exact sequence actually and used it. Let me just explain a little bit what the, running out of time, very quickly, what is the setup here. I'm looking at pointer eigenclasses. The orthogonal group maps into the homeomorphisms of RD. And we know that if you let D go to infinity, then both of these cohomology rings are just generated by the pointer eigenclasses. So you might ask yourself, well, what about if I restrict myself to the n-dimensional case? What happens to the relations that I know in this smooth case? And of course, the assumption was that, well, you know, there seems to be no reason why not to expect exactly the same sort of relations to hold also in the topological case. And this is something that I tried to prove for quite some time, but then I realized that's actually not correct, and proved that these relations don't hold. And indeed, then Randall, Williams, and Galasius managed to prove that this is actually, there's no relation whatsoever in the higher dimension. So even for dimension D, I can fix the dimension, and I have all these pointwise eigenclasses, and there's no relation. An upshot of this was, you can look at the diffeomorphism of these odd dimensional spheres, and again, this is an injective homomorphism. Okay, so we now have already seen that this helps us to understand the diffeomorphism of spheres and disks. They're actually very closely related. Diffeomorphism of sphere are just the diffeomorphism of the disk cross this term. And of course, when these are trivial, then we are in low dimensional cases. And only just recently, this is a sort of Smale conjecture, and recently Watanabe showed that the Smale conjecture is actually wrong in dimension 4. So I think that is still a preprint, so I should be careful. Right. In the interest of time, let me just move on very quickly. What else might be proved? Okay, this is actually a continuation. Conjecturally, at the very least, we now have a complete description of these homotopy groups rationally, both in even and odd dimensions. Randall Williams talked about this in his ICM talk 2 years ago, and it's a good survey. And let me just finish on another completely different problem, namely the question about positive scalar curvature. So we start with a manifold, we have a metric. The metrics normally, of course, are contractible space, but if you look at positive scalar metrics, that is a completely different thing. It's a subspace. And indeed, Hitchen in the 70s proved that, you know, there are many components, or it's not just one component, I should say, and the fundamental group is non-trivial, but little was known. But now with these sort of methodologies and techniques, Ebert and Randall Williams in particular were able to analyze and show that these spaces are at least as complicated as detected by the index difference on spin manifolds. So mapping to K theory. Let me stop here, and thank you very much.